All right, this video is going to be going over the properties of limits and how we evaluate limits with direct substitution. And so when we do that, essentially what we're doing is we're taking the x equals a value and you are plugging in to that function. If you have a linear function like this right here, then our actual f of x is x. And so as x goes to a on this line, well, that's just going to be your output, a, because it's the line y equals x. So we're basically just plugging in x equals a into this line because that's a continuous function, and so we can just plug in the limit and the function value will be the same. And we'll talk more about continuity in our next video. If you just have a constant, so a number, then that's going to be a horizontal line. So anytime you plug in some a value, let's make a negative this time, anytime I plug that in, I'm still going to get whatever y equals c is. So some examples here, if I want to find the limit as x goes to 2 of the graph of x, that's just going to be 2. If I want to find the limit as x goes to 2 of the graph y equals 5, that's going to be 5. And so we're going to use that in order to look at some of our limit laws. Basically, what you need to know is limits follow linear combinations. And so if we know that this limit is L and this is M, if we want to add the limits, well, you can just add L and M. If we want to subtract these two functions, I should say, add these two functions or subtract these two functions, you can just subtract their limits. If you have a multiple, then you can just take that multiple outside of the limit and do the limit, c times that limit value. If we look at this example down here, I'm going to go ahead and do those three in this example. So since I have 4 times x plus 2, what this tells me up here is that I can make this 4 times the limit as x goes to negative 3 of x plus the limit as x goes to negative 3 of 2. I'm using this rule here first to say that this would be the limit as x goes to negative 3 of 4x plus the limit as x goes to negative 3 of 2. I used that one first and split that up. And then I said, oh, okay, I can use this rule here in order to multiply and take that 4 outside and then multiply to the limit. I'm using the basic properties we just did. This is going to be 4 times negative 3 plus 2. But this is also the concept of direct substitution. If I have a line 4x plus 2 as my function, then I can just plug in negative 3 and notice that's what we're doing here. So the limit laws exist. You don't necessarily need to memorize all of them. You just need to understand that limits follow normal function rules. Okay. Same thing with product and quotient, as long as m's not 0 here, obviously. Powers and then roots are just specific powers because you can rewrite that root to the 1 over n, and so these two laws kind of go together here. All right, let's go ahead and look at a couple more examples here. So this is going to be an example of that limit law for the division. So if you want to think about in this example, if this is like my p of x, and then this is my q of x. Now the first thing we do want to make sure every single time is that that denominator function, okay, is not 0. Trying to get my eraser there. There we go. Okay, that denominator function is not 0 at x equals 3. If it is, then we either are going to have a whole or a vertical asymptote. Okay, but so that's going to be that first check. So if I take 5 times 3 and add 4, I'm not going to do that right now. I just need to make sure that's not 0. Okay, that's true. All right. So what this says is we can just take basically the limit of the top and the limit of the bottom by just plugging in a. So I'm going to say this is 2 times 3 squared minus 3 times 3 plus 1. And then here I am going to go ahead and evaluate that denominator. And I got 3 because that's where we're taking the limit from right here. All right, 2 times 9 gives me 18 minus 3 times 3 is 9 plus 1 over 15 plus 4. And so I end up getting, let's see, 10 over 19. And I'm going to just leave it like that. I'm not going to worry. I mean, there's no way to simplify that, but I'm not going to worry about doing decimals or anything like that. Like, I'm just going to leave it and we are good to go here. Okay. Sometimes when we go to plug in for this direct substitution, though, we're going to end up having some issues, especially when we're looking at rational functions. So if I can try to algebraically manipulate that function where except at a, because we're taking this limit as x goes to a here, right? So except at a that these functions behave super the same everywhere except a, well, then the limit of the original function must be the same as the limit as the one that's behaving just like it, just not at a. Let's look at this as an example. So remember I said if you have this rational function, the first thing you should do is plug in 1 into the bottom. Oh no, like that's 0. So we have a couple things potentially going on here when that's the case. Either this is a vertical asymptote situation or it's a whole. Let's check for the whole first. Can I factor the numerator? And the answer is yes. And then second part of this, is the numerator's factors one of the things that can cancel with the bottom? Second answer is yes. Notice that is the a value that's causing this issue, right? So everywhere except at 1 in this problem, this equation looks just like this line, and you can graph it if you want to, like on Desmos or whatever. Y equals x plus 1 with a whole at 1. So this function I'm looking at behaves just like this line everywhere except 1. Well, then their limits are the same. Okay? So I'm going to say, oh, well, now I can just say, let's take the limit as x goes to 1 of x plus 1. I'm going to plug that in, and I'm going to say that is 2. And that is my answer. Let's look at another example here. What happens when I plug in 3? Let's see. So I get 2, 3 squared minus 5 times 3 minus 3. Do I get 0? I get 18 here minus 15 minus 3. Oh no, I get 0. Okay, is there a factor in the top that cancels with a factor in the bottom? That is my next, like this is my next check. Okay, so let's see, limit as x goes to 3. I'm going to factor the top. And I'm going to factor the bottom. Now, here's a little bit of a trick. I need to figure out, right, x can't be a. So x cannot be equal to 3. And so I'm trying to figure out that's like the problem area. Notice I have a factor of x minus 3 in the top. Let's see if we can get a factor of x minus 3 in the bottom. So if I were to do that, I know this has to be a 2x and an x. And if I end up making this x minus 3, does it make sense with the denominator? So what I mean by that is like, okay, -3 factors would be -3 and +1. Let's double check here. -6 on the outside, 1 on the inside. Yes, those are the factors. So I have a hole in this graph at x equals 3. This function is going to behave just like x over 2x plus 1. Now, I would have a vertical asymptote on this function still. So if you were to plug this in, I do still have a vertical asymptote of -1/2. That denominator is still 0, but I don't care about that anymore because it's not at x equals 3. So I can just plug in 3 now. 3 over 6 plus 1. So I get 3/7 and I'm done. All right, we have one more example here in this video. Let's look at a piecewise function. So on this piecewise function, notice I have x plus 1 if x is less than 2, x squared minus 4 if x is greater than or equal to 2. My first one here is I want to approach 2 from the left. So think about numbers to the left of 2. Well, that means I must be looking at this first function. So I'm just going to plug that in. That's the function that I'm looking at. And because that's the function that's defined from the left of 2, I'm just going to plug in direct substitution. 2 plus 1 gives me 3. All right, now let's look at from the right of 2. So x greater than or equal to 2. Well, then I would have to look at this one. So the limit as x goes to 2 from the right of x squared minus 4. I would plug this in. I get 4 minus 4. I get 0. Now if you're like, but we're not supposed to get 0. It's fine. It's a numerator. I can have 0 in a numerator. Totally fine. This output is 0. Now notice these are not equal to each other. We'll talk about discontinuity again in the next video. But one thing that I want you to note is that if you were to look at a graph of this, 1, 2, as I approach 2 from the left, I must be going to 3. Now I used an open circle because of the domain here. As I approach 2 from the right, my output goes to 0. So this is going to be a jump. Okay, so even if you really don't know what parent function graphs look like, which you should at this point, but if you don't, that's kind of okay. Like you can plot the point 2, 3 with an open circle because of the domain. You can plot the point 2, 0 with a closed circle because of the domain and be like, oh, those aren't the same number. I'm going to have a jump discontinuity at x equals 2.